I'd like to thank you, Piers and Rajiv, organizers, giving me a chance to participate. I have been enjoying a lot and also speak about one of my recent work about the Kitaev materials. I mean, we had a lot of discussion yesterday, so I will probably skip some of the slide that I have prepared, which overlaps with some of slide that we have seen yesterday. So this work, in fact, has been a kind of history for me, at least. So it has involved a lot of theorists. Those who are in the box here are my former student, and some of collaborators outside the University of Toronto or inside the University of Toronto. And I had a long collaboration with experimentalists, and luckily enough, and some of those are related to not just the Kitaev, but also spin-orbit coupling generally in strongly correlated systems. So today's talk, it was mainly done by Eric Sorensen at McMaster University, built based on the Jeff and Andre and Jacob, my former and current student. Okay, so as I was talking before the session start, I was thinking about like, okay, what would be a good, title? And I thought that maybe I can just come up with Kitaev materials governed by Kitaev physics, because I doubt it. So you can see that it comes with a question mark. So it comes with a little bit of my perspective. And I'll probably try to tell you why I think that's the case. So in some sense, we know that in materials, so I'm talking about real materials, and Kitaev interaction is not our only interaction. And we do know that there are other interactions. And one may ask, are they minor players? And everything is more or less, dynamics or high energy and so on are governed by Kitaev is one of the questions that I've been thinking about. In other words, they might lead to a magnetic order, but in some other interactions, maybe not. So in the material, we do know that there are Kitaev interactions, but is there a possibility that other quantum spin liquid different from Kitaev spin liquid does exist in Kitaev material? So that's what I'd like to address today. Okay, so here is my outline. I will first talk about the Kitaev materials. Basically, I think Kitaev materials are the physics of Kitaev and another bond-dependent interaction, which is called gamma interactions. So this I just call KG model. In any case, so that's requires a bit of microscopics. We have to go deep in the microscopic theory and try to see where the Kitaev comes from and why that inevitably cannot avoid, well, basically, once you have a Kitaev, why we cannot avoid this other interaction, and what is the ground state such gamma interaction is a hot topic, and it has been a controversial. So I just want to tell you the excitement as well as puzzles. And then, well, since this is the difficult problem, I'll reduce the dimensionality because it's no longer exactly solvable. And reduce the dimensionality, meaning that we can probably get some insight from the 1D chain or ladder and thinking about like, is there a disordered state? Are they possibly a quantum spin liquid? Is there a field-induced disordered phase? So I'll first begin with a bit of microscopic theory of those materials. So this is the slide that I'm going to skip because we've seen this interaction many times, and it's exactly solvable models and ground state EG2 spin liquid with Majorana and Bison excitations. And the candidate material, we've also seen it yesterday. Basically, there are honeycombs of iridate and ruthenium trichloride, which basically form a honeycomb. Okay, so to understand the physics of these materials, we need to understand the origin of bond-dependent interactions and then ask ourselves, what do we learn from this microscopic theory? Like, what is the interaction that, why is it Kitaev? What else do we have? And once you have what else, what is the ground state that we are looking at it? And why they are dominant and what phases that we are ending up by this type of the spin interactions. So bond-dependent interactions are coming from the various conditions. One need to have multi-electrons, orbital degree of freedoms, and spin-orbit coupling, which has been kind of known. And I'll be restricting myself in the J-effective half, which you can get it from a T5 with where T2G has a strong spin-orbit coupling. But of course, bond-dependent interaction is not just a constraint to the D5. In principle, if you have a D2 or a D7 or a D8, depending on the situations, one can also generate some bond-dependent interaction, which can be dominant in some of this magnetic or non-magnetic Mott insulators. So I'll be restricting to the effective half, which is relevant for the ruthenium trichloride that we've heard a lot about this thermal transport. So to understand the bond-dependent interaction, we have to look at the wave function, because we know that the super exchange or any of those exchange process is based on the wave functions. So the effective half is made out of this T2G orbitals. And here the red color is the spin up, blue is the spin down, and XZ, YZ one-dimensional looking wave function can be combined. And you can see that LZ is either +1, and if you look at the JZ of -half, LZ is -1. So these are basically having a finite angular momentum, which is very important. So XY orbitals has LZ 0, but XCYZ comes with this imaginary, and you have finite angular momentum. So bear that in mind, and then let's look it up. So here is the ruthenium trichloride with ruthenium making honeycomb, and chlorine, which has the p orbitals surrounded, and we are having an edge sharing. And this red, I'll call the Z bond, and see what happens in this exchange process on that Z bond. So I come with a magnify here and looking up the bond, and there are two paths going through the p orbitals, bottom and a top here. And if you look at it here, so in this case, imagine that the XZ can hook to the p orbitals here, and then p orbitals here, electron can hook to another one of those 1D orbitals, and I'll call that as the T naught, which is the effectively TP d pi squared divided by delta PD, where delta P is the atomic potential difference between the p and d orbital. So far looks like very conventional, but in fact, that is because the wave function that we're looking at is going to be, say, effective half, is not that straightforward. So this type of the moment, the p orbital kind of indirect or p orbital mediated hopping is only, there are only one kind in the Z bond. So here's a Z bond again. There is no hopping between the XY because the p orbital is a plus and minus, because of mirror symmetry between the Z and minus Z, this is 0. So there's an interorbital between XZ and YZ, or YZ and XZ. That is only one that is finite. So if you go through that, of course, YZ to XZ, or you can go back to the YZ to the XZ, or XZ to the YZ, bottom or top, it doesn't matter. One can see that this interorbital hopping between the XZ and YZ going through the p orbitals, rewrite them in the basis of this LZ equal to ±1. Remember that the J effective half contains this angular momentum being 1 or -1, LZ 1 or -1. So if I have a hopping between the XZ to YZ, which is written in this tight binding form here, and then rewrite in the basis of LZ ±1 eigenstate, you note that the hopping from these two different interorbitals, the non-conserving orbital process, will have to change angular momentum by the 2. So delta LZ is actually a ±2 in this process. So that means because spin is conserved, delta JZ effect is going to be ±2. So this process, in fact, involves, again, this orbital non-conserving process involves the finite, the change of angular momentum, Z component is a ±2, and that involves, obviously, not in the, so here's a site I, and then the other one is site J, site 1, site 2. It'll involve the next site of the higher state, which is separated from the j equal half, the plus minus half is separate from the plus minus 3 half. So that's the one thing. And then you can immediately tell that there is no Heisenberg interaction. So it is not that the path is canceled out. It is because there is no projection onto the j effective half that there is no Heisenberg term. Okay, so I want to make that clear. And it's not as simple as just involving the excited state here, because we already have site on the other side here. There's one hole is occupied. So when I move the one hole here, this is a two particle, the excited state. And that two particle excited state is going to have a two different kind. And one kind can be written as the two particle triplet and two particle singlet. So two particle triplet and two particle singlet, this excited state has a different energy, which is set by the Hund's coupling. So this term here, Kitaev term, is not finite unless Hund's coupling is finite. So it involves not only spin-orbit coupling, but also finite Hund's. And you can see that to going through this process, in fact, the only term, exchange term is allowed, is going to have this Ising interaction between SZ and SZ, where S is in fact the effective half operator. Okay, so this is the wave function connected by the exchange process, and its interaction is going to be a Kitaev. So when you have only a p orbital dominant or p orbital driven, super exchange driven hopping, then we just note that the Z bond is going to only have this Ising term. Now, that's all I need to do, because once I apply the C3 rotation operator here, then the X bond, instead of having XZ, YZ orbital, I'll have to deal with XZ and XY orbital and vice versa. And then if I choose the quantization axis along the Z, the interaction that I end up in the X bond will have SX, SX, and the Y bond will carry the SY, SY. So that's where the Kitaev interaction is popped up. So if you want to make a material with the Kitaev dominant interactions, then all we need is in fact just to have, just ignore the direct interactions, direct hopping. So make them far away. Somehow we engineer them to have only a inter-orbital hopping. This will be a way to generate the Kitaev interaction. But another thing to notice is that this interaction comes with the minus sign here. So it is a ferromagnetic Kitaev interaction driven by interorbital hopping. Okay, now what about the other interactions? Well, we always have a direct hopping between the this T2G orbitals. So obviously, if I have just the orbital conserving hopping, then this type of the direct hopping will give me a Heisenberg interaction. So that's a textbook example that we have learned. All right, good. But so once I have a direct hopping as well as indirect hopping through the p orbitals, I have a Kitaev interaction and Heisenberg interaction, and that has been the case for a while. But we have noted that that's not always the interaction that we have. In fact, that there is another path that one could take, which is the one direction. The electron hop from one of this the orbital YZ to the XZ. So that involves, again, just like a Kitaev origin. So this will give me something looking like Kitaev. It's I come back to the another T naught, but I can also have a pass, because this wave function, remember that it's a linear combination of T to G. So in fact, I can hop to the XC, and then my orbit, my electron can be some equal combination of XC and XY. So I can definitely take a XY pass to a XY orbitals. So that means it's an interference between the indirect and direct hopping, and that generates this so-called gamma interaction. So this is a Z bond. In this Z bond, going through T naught, which is the indirect hopping through the oxygens, or in the XZ and YZ, just the orbital changing hopping. And then there will be a direct hopping between the ZX, or XY, they come with a different sign. But because of the orbital lobe, TXY actually has a negative sign from the ZX, XZ, because one is the pi bonding and the other is more like a delta-like. So they actually add up. And so this term is very large. And again, the process involving is that the Z component of J effective has to change by ±2. So the excited state, the virtual process of the excited state involve two particles, again, triplet and singlet, and they come with this formation. So Hund's coupling is important to come to generate the gamma. And as it is written here, gamma interaction is actually antiferromagnetic. And that's also quite important. So the generic spin model, ideal honeycomb contains the three terms, just the nearest neighbor. Of course, one can think of a second and third nearest neighbor, but within the nearest neighbor, there are three terms, and there are two bond-dependent interaction. So Z bond here will take a ZZ here, a gamma term will take XY, and then YX. So in other words, Kitaev interaction, we've learned that we've heard a lot yesterday, that it's an Ising interaction with the different directions, and that's frustrated. Gamma interaction is more like XY-like, so it's even more frustrated. And the one bond is XY, but this bond is YZ, ZX, and then this bond will take XZ and ZX. So it's quite a difficult term to handle. And when the dp orbital overlap dominate, then Kitaev and gammas are dominant and overshoot the Heisenberg terms. All right, and this was recognized quite early in the ruthenium trichloride. We've noted that in fact that the dominant terms are Kitaev and gamma, but gamma, the name was rather boring. So I think we are still calling Kitaev materials. So the idea is that, okay, we know that dominant interaction is Kitaev and gamma, and other small interactions such as Heisenberg and maybe other terms like a trigonal distortion induced other interaction called gamma primes and third, second, and so on will generate some magnetic orders. And so one can ask, what if I can destroy such a small, the magnetic order set by a small interaction, because those small interactions are going to be small energy scale. So if I have a magnetic order set by the small interaction, I'll be able to destroy them with some small magnetic field. And once I destroy those magnetic ordering, then the phase that I'm going to reveal is going to be the phase that's set by the Kitaev and gamma interactions. So the question is, what is the Kitaev plus gamma model with or without the magnetic field? So, and this has been very controversial. Okay, so it's a very simple model. I have Kitaev interaction and gamma interaction. These are both bond dependent as I move along the three bond, and there is a field in it. So even pure Kitaev model is exactly solvable. As soon as I put the field, even without the gamma, this is numerically done. And there was an interesting proposal or calculation that there's a U1 spin liquid appears under the field if there is an antiferromagnetic Kitaev interaction is the one that's dominant. And pure gamma model without the Kitaev is completely controversial. You can see a list of the studies, and this one is growing. So many of those suggest that this is in fact disordered, and except the one over here, which is exact magnetic order using a variation of Monte Carlo, but in this is a variational, so they have to come up with some variational wave function, which probably is biased. So many of these studies has been suggest that there is a non-magnetic studies. And gamma model itself, classical spin was also studied, and it was shown that it's like a classical spin liquid where the degeneracy is growing as a macroscopic numbers. So I was thinking maybe we can restrict ourselves and thinking about why don't we start from a small size? Well, in a sense, the small geometrically restricted, but we can take a much larger size of system and ask ourselves, in this Kitaev and gamma model, is there a disordered phase, or there is a disordered or field-induced disordered phase? If I have this magnetically ordered state in the chain and ladder, I would expect to be magnetically ordered in the 2D system. So maybe not a bad idea to begin to understand, to get some insight from a small low-dimensional system. So any insight from 1D, in fact, that this was also done by the pure Kitaev model. So you can imagine this is a honeycomb here. If I cut it one leg, that will be a Kitaev chain, which is Kx, Ky. This is also exactly solvable, and one can show that using just the Jordan-Wigner transformation. This is just a map to the free fermion model. And the ladder is also looking at like, you can distort this into the brick wall And if you have a two leg, it will correspond to the ladder here. So that's the model was in fact studied in this paper quite a while ago. And you can see that this is a two-leg ladder. And here is the function of kx divided by kz. And this is ky divided by kz. So isotropic limit is falling into in this point here, where this 1 and 1 meet. And that will be an isotropic Kitaev model. And these are anisotropic Kitaev model. And they have shown that there is a phase transition, which is set by this line here. And there's another line here. And one can show if you cross across this dashed line here as a function of k minus, is a kx minus ky difference. So cutting along this line, you can see the clear two peaks appears. And so here's a two phase transition. And each of those anisotropic part can be characterized by the non-local string order parameter. So this is a one-dimensional system, and one can construct non-local string order parameter of this particular part. And they have shown that there's a finite non-local string order parameter exists in this two of those, but it looks like it's disordered inside this isotropic Kitaev point. I'll show you that that's not the case, but in any case, it was suggested that in the ladder, this transition boundary is rather important. And then one can build up just to make more leg. So the earlier one was a two leg, m equals 2 is actually a four leg, 6 leg, 8 leg, infinity. So here's a Kitaev model that we know. You know, we've seen it like a triangular shape, but this is just a drawing in terms of kx divided by kz and ky divided by kz. So the ladder is the one that defines this boundary, phase boundary between the Kitaev spin liquid of isotropic one and then anisotropic one was in fact bounded, already found in the two-leg ladder. And if you make the many leg, combine them and more, then what happened is that this boundary that's set by the ladder is not changing, but what happened is that this phase, there will be a more phase boundary will appear and so on. And then these things are going to be filled up. And to the limit, in the two-dimensional limit, this will be a gapless Kitaev spin liquid here. And AX, AY, AZ is going to be a toric code with the gapped Kitaev model. Okay, so in fact, that the Kitaev model itself also has the ladder limits where things one can understand a lot about it. All right, just a little digress from the ladder. So we have done the Kitaev Heisenberg model, for example, and one can show that here's a Kitaev phase here, and then here's another Kitaev phase here, and here is a Heisenberg interaction introduced, and depending on the size of Heisenberg interaction, you have a stripy, and because this is ladder, there's no antiferromagnetic order, but it'll be a round singlet in the ladder, and then here's a zigzag, and here's a ferromagnet. And this phase diagram is completely identical to the 24-side C3 symmetric honeycomb lattice. Only difference is that long singlet here is going to be antiferromagnetic, and a little bit of this phase boundary will shift around, but physics is exactly the same. So at the level of the small ladder is already, physics is captured, and we know that the Heisenberg interaction introduced the ordered phase. On the other hand, another thing is that, as I said, antiferromagnetic Kitaev or ferromagnetic Kitaev was described as if there is no non-local string order parameter, but in fact, one can find, and it's very complex one in here, but in any case, in the ladder, one can find the topological order here in a sense that non-local string order parameter, which becomes long-ranged in this within this ferromagnetic and antiferromagnetic Kitaev. Okay, now let's go back to the Kitaev-Gamma model. This is much more, looks complex, but in fact, there is a symmetry that one can use. So if I use so-called six-site transformation, in other words, I just change X, Y, Z to the tilde basis through this six-site transformation, one can map the Kitaev-Gamma model in a minus Kitaev minus gamma, but then see that this alpha beta, because gamma takes the ZZ, then alpha beta take XY, but through this six sublattice transformation, in fact, one can take tilde takes the alpha alpha and beta beta. So you can see that through the six-side transformation, once the Kitaev and gamma has the same sign and equal magnitude, then this maps to the Heisenberg model. So when they comes with the same sign, it's the problem becomes rather simple and straightforward. And you can see, for example, if I want the chain, xy will map to xzy, xzy, and so on. If the interaction is the same with the same sign, this will be nothing but a Heisenberg model, six sublattice in six sublattice new basis here. Okay, good. So if I have a chain in the in this model, I'm going to set the parameter here. Sorry that I have changed the Kitaev on the right and left now. Kitaev is a cos phi and gamma. The gamma is a sine phi, and phi is measured starting from here. So here's an antiferro-Kitaev, antiferro-gamma, ferromagnetic Kitaev, and ferromagnetic gamma interactions. And when they are equal in magnitude, which is this point here, will map to the Heisenberg equation and comes with a opposite sign. So this will mapping into the ferromagnetic Heisenberg. It's a 1D system ferromagnet. It's ordered here. And this will mapping into the antiferromagnetic Heisenberg, and it's actually gapless. And in the 1D case, without the Z bond here, in fact, there is additional transformation that one can work it out. It's called the three sublattice transformation, which I didn't show, but one can map that this point can map to here exactly, and that point map to here. So in fact, that this phase diagram is symmetric between the north and the south. And what happens is that this ferromagnetic Kitaev is in fact simply not even a phase. It is, remember the Kitaev model is 1D case, it's a free fermion model, and it's just a phase transition point. So it goes from a one gapless SU to level 1 actually, and back to another gapless mode here, phase here, and these two are ordered state. And in fact, the antiferro-Kitaev survives in a finite window in this. What happened in a ladder is that if you go in this format here, it's more interesting. So again, when they have coming with the same sign, here's a Kitaev gamma equal to each other. It's a ferromagnetic Heisenberg, so it's ordered state here. The spins are ordered. And here is antiferromagnetic Heisenberg model on a ladder, which is wrong singlet again. And well, we found that this area, the orange area, is actually ordered. So this will remain to be ordered. Purple area here is antiferromagnetic Kitaev. So Kitaev phase survives here. And there's a yellow part which starts to show up in the ladder. And this is the ferromagnetic Kitaev. And this part, the green area, which include gamma, antiferromagnetic gamma, and some part of the ferromagnetic Kitaev is actually a disordered state. So there are 1, 2, 3 disordered state. 2 of those are Kitaev, and 1 of them is, in fact, gamma, including the gamma. It's a gamma disordered phase. Okay, so we have found that there are 3 disordered phase with the 2 of the Kitaev, and in the 2D limit, this thing here, positive and negative Kitaev, will mapping into the Kitaev spin linkage. On the other hand, in this area, which is much wider phase space here, is going to be a some disordered state, and we are basically speculating that this might be a gamma disordered phase. Okay, so now we wanted to look this up with some finite magnetic field in the ladder geometry. And I'll show you like what happens if you add a more leg, like if you have 4 leg and 5 leg, or what about little other studies, more of 2-dimensional limit. So so I just add a Zeeman-Thom. We have some discussions about the magnetic field, magnetic couples through the Zeeman-Thom, and that's it. So this is going to be Zeeman interactions to the S star and H. Again, here we will restrict ourselves for the magnetic field along the 111. 111 means it's a C-axis, which is perpendicular to the honeycomb direction, because here the Z quantization axis is determined by the octahedra that's surrounding the ruthenium atom or iridium atom. and that direction is not the c-axis. So it's not the same. So just bear that in mind. H is along the c-axis. And this was done by DMLG as well as IDMLG with quite a big bond dimensions with a lot of 200 different sites. So it's a very large system. So here's what we have. This is actually quite complex.
You've hit the 30 minutes.
Yeah, okay, good. I'm almost done. Good. So this is showing you the so-called single copy entanglement. Entanglement susceptibility. Basically, you take the largest eigenvalues of transform matrix and take the derivative respect to the parameters. The x-axis is the phi. Remember, the k was Kitaev was cosine phi and gamma was sine phi. So at this point where phi was equal to 0, here's Antiferromagnetic, and here's a ferromagnetic, and here's Antiferromagnetic, and here is ferrogammas. Most of material that we have looked at it actually falling into somewhere along this line here, from the ferromagnetic interaction to antiferrogamma around this area here. So they are sitting in the very interesting area, and you're taking those derivative, and these colors are bright red, are referring to some phase transitions here. And you can see a lot of these bright colors here, and we think that these are mainly coming from some kind of incommensurate orders. So I don't want to bore you with a lot of this 15 different phase. Let's focus on the one that are not magnetically ordered. A lot of these are actually magnetically ordered. So the one that is not magnetically ordered is the one in here, which is we know that it's antiferromagnetic here. And there is one in here, which is a ferromagnetic spin liquid here. Here is the disordered phase, which are governed mainly by antiferrogamma interactions here. And then there is a field-induced disorder phase here. Okay, if I'm just focusing on this area. Near the antiferromagnetic, there is something more interesting going on, but if I have time, I'll address that. So, okay, good. So now let's look at near the ferromagnetic Kitaev and antiferrogamma area here. Just look at the bit of details here. And as I said, in this ladder, we see that Kitaev phase, it's not a spin liquid yet because it's some kind of described by some kind of non-local string order parameter. Will confined along within a very tiny window here, and then there's this disorder state. This is another disorder state, and this is actually a field-induced zigzag phase that appears. And what happened is that this was along the field along the 111. If I tilt the field from the 111 and make angle of 5 degree and the 10 degree, then what happened in this disordered phase here, they will shrink. So this area, this is a spin-spin correlator. So that's why the colors are different. This area here is going to get smaller and smaller as the angle goes away from the c-axis. But you start to see a lot of this partially polarized state that still remains. It's not, we cannot get rid of them. And the Kitaev spin liquid are confined within here. And this disorder state here, we have added a small trigonal distortion. In material, it's a trigonal distortion. In theory, it's called the gamma prime interaction that is allowed by the trigonal distortion, which exists in real material. Then you can replace this disorder state, become a zigzag, but field-induced disorder state will remain. So this one is going to survive in a certain angle away from the c-axis. So these are the ladder study. What happened if you make the 5 leg, and this was also done, 5 or 4 or 6, and it's consistent that Kitaev spin liquid or Kitaev phases are surviving on a very tiny window here. Again, here is the minus K and gamma. These people has plotted, backwards. So you have to see that the parameter space is rather different. Here, the gamma is on the left side, the Kitaev is on the right side. Here is backwards. Left is Kitaev and gamma is actually on the right-hand side. So in the middle, you can see exactly the same, that disordered and then zigzag and then disorder state. If you include that trigonal distortion, it's again the same happens. Kitaev is limited here. There is a zigzag order appears, and there is this disorder state, which are called NP, meaning pneumatic paramagnet. Apparently, they have found that there is some kind of bond energies which are anisotropic. So that's what they have found. So apparently, most of numerics is speaking that there is some kind of field-induced disorder state. At this point, we do not know exactly what the nature of disordered phase that appears here. The one which is this disorder state that without the trigonal distortion. So I really wish that somebody can make this crystal without less and less distorted. And this will be indeed more of this, non-magnetic state. In the latter, this in fact has the non-local string order parameter. So I suspect that this will be likely a quantum spin liquid, different from the Kitaev spin liquid. And I do believe that in particular, ruthenium chloride 3 is sitting somewhere around here, which are governed by this physics rather than maybe not rather than a Kitaev. This one, if I have a time, I'll probably just quickly go through. This is near the antiferromagnetic Kitaev. In fact, there are two other disordered phase without the magnetic order. This is the area where people claim that there's a U1 spin liquid. In fact, field-induced U1 spin liquid here. This eta, beta, and mu, these are all ordered state. It's some kind of incommensurate or commensurate ordered state. And this area where people claim a U1 spin liquid indeed has no magnetic order, but it has a finite scalar chirality. So there's a staggered chirality and uniform chirality. So in fact, it has quite a rich physics in the ladder alone. So there are still open question. I think I have given you some speculative kind of perspective that these Kitaev materials are much richer than just the Kitaev physics, even in terms of quantum spin liquid, not only leading to a lot of different magnetic order state, but still, I don't think I can definitely say that what is the nature of Antiferromagnetic phase, nature of those chiral phase that appears around the Antiferro-Kitaev is still need to be discussed or determined. And hoping that one day we have materials with the dominant Antiferro-Gammas and Antiferro-Kitaev would be kind of interesting things to check. So with that, I'll just leave my summary here. And thank you for your attention.
All right. Thank you very much, Hae-Young. So we have time for questions. Steve was first, I think.
Yeah, thanks very much for your nice talk. I have a couple of questions. One is, do you have any idea what the effect of three-dimensional interactions is on this phase diagram? And also, what can you say about the likely nature of the magnetic excitations in this sort of gamma spin liquid?
Yeah, so for the gamma spin liquid, the magnetic excitation, so there are two questions. One is the, let's begin with the gamma interaction case. So this was, in fact, so for example, if you are somewhere near here, so this is zero field, the spin liquid, the spin excitations has been discussed in these papers, I believe, in this Matthias Golke's papers, as well as many others earlier. Sorry that if I missed some references here. And in fact, that they are very much like what you have seen it. What you're those shapes of the star shapes and so on. So they are very much like what you have reported in your neutron sketching. Now, in terms of the three-dimensional coupling, we know from the structure studies that the layer couplings are very weak, van der Waals, and that leads to those stacking fault and so on. But I do believe that the coupling between the layers is important, in particular when you have those the field in the planes and so on. And the reason for that from a chemistry point of view, because from an exchange path, earlier when we were looking at ruthenium chloride 3 in the very, very early beginning, that the structure was a P3-112-121. So you have three layers which are having some 3-1, the glide axis along the C axis. And in that case, when we calculate the exchange parameters, we actually end up with the Antiferromagnetic, but Antiferro-Kitaev as well. And the reason for that is because when you are changing or stacking, the chlorine positions actually start to change, and that is changing a super exchange process. The value of the exchange process is going to change. And Kitaev interaction, in fact, has a two contribution, which I didn't discuss. There's the contribution coming from the super exchange and also coming from direct exchange process. And they come with opposite sign. So once you have two different contributions which are dominant each other, and one can cancel out, and one can change the Kitaev interaction from negative to positive. So in fact, depending on the layer stacking, in some material, we have found the Kitaev was actually a positive, and then someone, which is a C2M and R3 bar, we actually found the ferromagnetic Kitaev. So that meaning that depending on the stacking that we have, we might be able to change the size of interactions Kitaev moving along these directions, but the gamma interaction is always positive. So I don't know exactly how to put the interactions between them. I mean, it's probably going to be some Heisenberg interactions there. But what I'm trying to say is that when you have a stacking, chlorine positions are slightly different, and that makes even affect the two-dimensional exchange interactions.
Thank you.
All right, so you have several other questions. So Rajiv first, and then Andrea, and then Piers.
Yeah, I was going to ask about the your assertion here that the materials are away from the Kitaev spin liquid phase and more in a different spin liquid phase. What about all the studies about proximate spin liquid that show really quantitative comparisons between the spectral functions at high energies and high temperatures with the Kitaev-Majorana description? I mean, is that purely an accident?
Actually, except the half quantized thermal Hall conductivity, every other experiment that I am aware of can be explained by the area around here. So the proximity to the Kitaev.
But we don't have any calculation. You know, you can do small size numerical calculation, but
no, this is yes, yeah.
There is the only system for which we actually have quantitative calculations in the thermodynamic limit is the pure Kitaev model, right? I mean, that's the only model for which we can really calculate properties completely rigorously. All the other calculations are very small size approximate calculations, right?
But if you
I'm saying that, is that an accident that a pure Kitaev type description works?
Pure Kitaev, no, it doesn't work. It depends on what do you mean work. So for example, let's say if you look at the anisotropy between the system, like so you have an in-plane. So let's think about the magnetic field dependence. Okay, let's just think about the magnetic field dependence. So one can apply the magnetic field in plane and the c-axis. As soon as I add the magnetic field, you cannot calculate anything with a Kitaev interaction, because magnetic field couples to the Zeeman interaction, not the way that Kitaev has done it. So Kitaev has done with hx, hy, hz divided by delta, where the delta is a Poisson gap with a sx, sy, sz. The reason for that is because he's assuming that Kitaev spin liquid is stable under the Zeeman interaction, and you can expand the Zeeman term, and then you will find that the first term that is coming in is going to be this hx, hy, that the one that break the time reversal symmetry, and that's the one that generate this bulk gap, and then you end up with this edge state that give you the finite half quantized thermal Hall. So what I'm saying is that in reality, you have to add a Zeeman interaction, because that Poisson gap is tiny, tiny, tiny. So we are not in that limits. We know that. So once you have thinking about, okay, in reality, I know that my magnetic field is 8 Tesla or 10 Tesla or 14 Tesla. I'm above the Bison gap of the Kitaev, unless Kitaev is like maybe 20 MeV or something. But we know that Kitaev interaction is not that big from the Stevens neutron scattering calculation, and many others has done it. And that interaction is about something like a 4 MeV or 5 MeV with a minus sign. And in that situation, that we know that that gap collapses and then you end up with something else. So especially we also know that in the case of many numeric calculations with the 24 side or many ladder or even 5 leg or many ones, if you have a ferromagnetic Kitaev interaction, which we think that's the case, a small magnetic field will completely destroy up to the very tiny field, and that tiny field isn't smaller than the Bison gap. So I don't think the experiment is speaking that it is near that Kitaev spin locator. So if one is getting some kind of quantum, so another thing is that why the gamma has to be finite is the field dependence that I was going to say. In plane magnetic field versus out of magnetic field, there's a huge anisotropy. And one might say, well, you can have a G factor, which can be very different between the G in plane versus GC, C axis. But we know that those G factors, anisotropy actually requires the trigonal distortion. And the distortion is not that strong. So if I forget about the trigonal distortion for now, then the gamma interaction, if you write them in the ABs, the in plane versus C axis coordinate, gamma is the interaction that gives you rigidity to the moment. So you can see that this along the field of H111, we understand why this disorder state extends so high, 1.75. This is in unit of K gammas. So it's a huge field is required to polarize it. And that is the case in the ruthenium criteria. And you can see that this partially polarized they survive even when I tilt it by some angles. So many of this is actually consistent to the proximity Kitaev, which is reported first by, in fact, Stephen Nagler with those neutron sketching. And you can explain that using some of this area here with the ferro and antiferrogammas. And strong anisotropy between the in-plane, out-of-plane can exceed beyond the G factor anisotropy. And what else? Thermal Hall, which we, as I said, except the half quantized values, that can be also understood from some of the topological mechanisms, which also requires the finite Kitaev and gamma interactions. So I think it is antiferrogammas rather large. And I don't need a big number. I actually need small. You can see that is how it is confined here. The ratio between the two is as small as less than 10%. I'm in the physics of these guys rather than Kitaev physics. Kitaev is much more fragile.
All right, Andre.
Ian, first a question of clarification to this graph, which I think maybe you just said. I was going to ask how stable is the Kitaev spin liquid part, and it looks from this figure on the right that it's tiny, right?
Yeah, to the right, it's tiny, yes.
Right. But then in the leftmost figure, you have a large region that says disorder.
Right, yes. So that is because, so that's a very good point. Yeah, and that's because if you look at this figure here is actually a susceptibility it's a single copy entanglement susceptibility. So if you look at the susceptibility, in fact, we missed it. We missed that there was no transition here. So it looked like a susceptibility was in fact continuous. So we thought that, well, there was no transition, which this one is in fact continuously connected to Kitaev. But then we look at the different quantities, which is the different eigenvalues. In fact, we start to see that there is a little cusp that appears. So which is consistent with these pictures here.
Right. And then what is the phase immediately above that?
Yeah, so this phase here is unknown. This is it's unknown phase here.
I see. So DMRG just doesn't give you any order parameters, and you're not sure what that
That's
is.
correct. That's correct. So it's the same for a tensor network here. This was done in a two-dimensional systems. And the only one they know is that it actually breaks the C3 rotational symmetry on the bond energy. But other than that, in fact, that the topology is unknown here. But all I'm saying is that these ones, we know that there is a non-local string order parameter. It's a disorder state with some kind of one-dimensional version of the topological order can be found. We are working on this one here. If there is any topological order that we can identify, even at the small ladder limit, which will be more positive to the quantum spin liquid. If there is, it is the spin liquid.
Thank you. And then one question, in everything you showed us so far, the field was along the C-axis. So if you wish, along the 1, 1, 1 in the local coordinate. So yesterday, if you remember, we heard from Matsuda-san say that we've had, depending whether he applied the field along A or B. Yeah. In one case, he appears to see a gapless feature. In the other case, Majorana gap opens up, as you would expect from Kitaev. So this begs the question, do you happen to know if anybody else or yourself did any studies for the field that would be along A or B axis in plane?
So we've done the in plane in these calculations. So obviously we can rotate it all the way to the in plane, which I have pictures. These guys will actually, this whole thing actually collapse. It's gone. So we don't have this disorder phase will survive in the in plane. Okay. A axis. B axis is more drastic. Everything is gone. This small window survives in the A axis, but B axis, nothing survives. It's completely gone.
Gone meaning replaced by zigzag?
Yeah, no, replaced by the Kitaev jump into the, so it's a tiny window of Kitaev will jump into the polarized state. This area here is just a polarized state, and these are partially polarized state and the polarized state. So kappa xy being a 0, by the way, along the b-axis is a symmetry. It's a symmetry of Hamiltonian, as so because my Hamiltonian does not break the mirror symmetry, and the field does not break the mirror. Therefore, you are supposed to get the kappa xy being a 0. Actually, that's the experiment that I suggest to the using Matsuda. So then you can rotate them. You can see that there has to be change in the change of the kappa xy sign changes. And I haven't done the calculation, but Yongbek has done some of calculations, and they have shown that the kappa xy, in fact, the change of sign under the A to a minus A, which is also understandable. But of course, we don't get the half quantized values because this part of anything, this polarized state, which might have topological mechanisms, then we are only getting some number to 1, as Kwanong has shown yesterday.
Thanks. Thanks a lot.
Piers and then Nick.
Yeah, I have a number of questions. First of all, you spent a lot of time describing the canonical transformations or second order perturbation theory that derives the model you're starting with. And all of those expressions involve energy denominators. And so my question to you is, if I start to increase the amount of charge fluctuation, if I push myself toward metal insulator transition, do you think there's scope for enlarging the region of Kitaev spin liquids? And before you answer that, let me point out one really important thing about the Kitaev spin liquid. It is a fundamentally new kind of gauge theory. It lies outside Wilson defined gauge theories in terms of area law and perimeter law. And the Kitaev spin liquid is actually outside that category. So it's a really new piece of physics. Unlike your approximate calculations here, we know it extends to 2 dimensions, whereas you do a tensor network in a narrow string, you don't really know whether it extends to higher dimensions. So I think really more effort should be spent on trying to make the artistry of the Kitaev spin liquid come alive than trying to kill it by looking at all the stamp collecting into all the other phases that surround it. Of course, there's a gazillion number of magnetic phases out there. So my question to you is there a way of enhancing the region of Kitaev spin liquid by enhancing the charge fluctuations? fluctuations?
Okay, so first of all, yeah, I would like to keep the Kitaev spin liquid. So it's not that I want to kill it. It's I'm actually more or following the material rather than beauty of. I mean, it's very beautiful, right? So I don't want to kill it, but what I'm saying is that once you have other interactions, you're not collecting the stamp of, you're not only collecting the stamp of magnetic order state, but you end up with some new phase, which may not have magnetic order, which might be a different quantum spin liquid. So let's say you have gamma interaction, which is instead of Ising frustration, I have U1 frustration. It's not exactly solvable, but we don't want to ignore it because it's a completely even more frustrating than the Kitaev interaction. So what is the phase of gamma interaction? And it actually dominates a lot of phase space. You can see that Kitaev interaction, as soon as you have Heisenberg interaction, as I showed you, it immediately kills. As soon as you have a small gamma, it immediately kills. So now back to your question. So I know that in the introduction of other interactions, which does exist in the actual material, I don't expect the Kitaev will be enormously appear unless, as Yuji Matsuda also have pointed out, that you can probably kill it by magnetic field, and you can probably have tiny window of Kitaev, which might be accidentally possible. So I'm not ignoring that possibility. Now, in terms of the metallic system, first of all, the
No, I didn't mean it. I meant as we approach a metallic system, as we start.
So as I approach the metallic system, so as I approach to the metallic system, then there's a huge charge fluctuation, as you said. Or first of all, it's not going to be a ruthenium criteria. It has to be something else, because I know ruthenium criteria gap is like a huge. It's a damn insulator. So it's very hard to change. Even it's extremely hard to dope it. You can't squeeze it because it's so fragile. So it has to be something else that one has to go up, make the U very small. And in that situations, you might end up with not only Kitaev being there, but Heisenberg and other interactions. So it's a very good question, but I don't have I don't have proper answer on that, I guess. But I don't expect that the Kitaev is the one that will survive, while maybe other interactions will come in, and you are dealing with the J1, J2, J3, and K1, K2, K3, and it's going to be a difficult problem, even more so.
It's a very pessimistic viewpoint.
No, it's a more realistic viewpoint.
Realistically, we're all going to die, but
no, why you say die? Because as I said, why don't you think about the gamma interaction and see what is the phase that is governed by gamma interaction? I mean, the name is wrong. I should have called it something else, but we call it gamma interaction. So, seems like it's not fascinating. And the reason it's not fascinating because we don't know how to solve exactly.
But also very difficult to extrapolate from a 1D system to 2D. How do you know it doesn't become magnetically ordered once you go to 2D?
I mean, that's why there is a tensor network studies as well as this 6-leg, whatever. I mean, this is what we have done it at most, given our computing power. And all of numerics as speaking exactly, so far, saying that there is this disorder state that in ladder, it has some kind of non-local string order parameter, just like a Kitaev ladder. Of course, I cannot say that it does not have magnetic order for sure, but we know that if you look at the, think about Ising model versus XY models. Ising versus XY is more frustrated, of course, and then gamma interaction is SX, SY, and it is it's changing along the bond. So if you start thinking about it, it's a much more fascinating model. It's just that we don't know how to solve it, and we are relying on our numerics. That's why it's not as fancy as you like.
Piers, somebody said, isn't the pessimist a well-informed realist or something like this?
Nick?
May I add something to that discussion? This is Yong Baek. So today there was new experimental paper appeared in arXiv. It's from Tanaka's group in Japan, and they apply a magnetic field perpendicular to the honeycomb plane up to 120 Tesla, very, very large field. And they found intermediate, disordered phase, they call a spin liquid, between 40 Tesla and about 100 Tesla. So that will be sort of consistent with this, many of these calculations where for variety of calculation found this, some kind of intermediate phase when you apply a field along the C direction instead of in the plane direction. So I think that's a more optimistic result, right? In contrast to more pessimistic conclusion. Looks like along the C direction field, right? Looks like there is actually an interesting intermediate phase. There may be a spin liquid that one of these calculation is suggesting.
Okay. I guess my point is it's much easier to be a demolition artist than it is to be an artist.
Well, I would like to be a more, I mean, in some sense, Kitaev is fascinating, but, you want to move on, right? So.
Sure, I agree, but the question is, should one use one's intellectual efforts to explore the vast range of alternative ground states? And it's much bigger than this model has. It grows and grows and grows. Or should you have some motivating principle for doing your exploration other than just showing that everything is different to what has been presumed? I mean, you've added these terms there, but we could add more terms. We could add 3 spin terms, 4 spin terms, 5 spin terms, right? And each one may give rise to its own great diversity of phases. And so presumably we're looking for fixed points and trying to understand fixed points. That's my only point. Anyway, yeah.
Right, but I mean, if I comment on that part, yes, you're right. You can add a second, third, and whatever the interactions, but we know that those become smaller and smaller. So as you said, that under that perturbation, small perturbation, we are looking for a phase that are kind of robust. And I'm saying that Kitaev is not the one, unfortunately, but Gamma is. I wish that I can, if we solve exactly, somebody solve exactly, this will be more fascinating than the Kitaev spin liquid. You can start thinking about how to solve it. It's a very difficult Hamiltonian.
No, but I think that the perturbations you're putting in of these additional terms may not be the right direction to go. That's why I mentioned charge fluctuations. Maybe ruthenium trichloride doesn't have a lot of charge fluctuations. But I don't know. But for example, coupling systems, one of the reasons we've got this in the same section as the samarium hexaboride is that there's a lot of potential for the physics defined by coupling the various families of Kitaev models and Yao-Li models to charge and conduction electrons. And so those may open up a fan which stabilizes the spin liquid type behavior, which perhaps aren't seen in pure spin models.
I mean, yeah, sure, possible. Yeah, so one should, I mean, as you see that from the beginning, that this is not just like a couple of years work. We've been looking at this, and ruthenium trichloride, I'm one of them who has suggested this is a Kitaev material as a candidate. So I'm very, kind of love into that particular material, because as someone like me who are looking for a material realization of some fancy phases like that. So I would like to see the Kitaev spin liquid in the ruthenium trichloride, because in fact, as I said, I'm one of them who suggested. And I have a sense that where that is, why that was particularly a right one to to investigate. But then as I go deeper and deeper, I realize, oh, there are other interactions, which is just unfortunately, not going to take the Kitaev but something else, and that something else is very, very interesting. And there are other directions people have taken. For example, you can think about higher spin Kitaev spin liquid. You can also think about like just like what you suggest, like other, let's say D7, the effective half can be also made by D7. There one can also think about the Kitaev spin liquid. And there are F electrons people have been thinking about generating the Kitaev spin liquid, and so on. And in fact, the direction that I think one should go is an antiferromagnetic Kitaev spin liquid that you should look at it. So in other words, if you want to make something stable and find the Kitaev spin liquid, better to find the Kitaev which are sitting in the antiferromagnetic. And even that, in that case, the zero temperature phase will be still tiny, but finite temperature, you have fan of those spin liquid, which might survive. And they might also survive in a field as well. So that might be another direction to look at it.
All right, last question from Nick.
Yeah, thanks. Sorry, this is a more concrete question from a non-expert, but I was wondering to what degree you can ignore the crystal field states, the EG states. I mean, you have this low energy J equals 1/2, but field, for example, could it mix some of the crystal field states and modify something, I would imagine. Has someone thought about this?
Well, yeah, I mean, EG state is because it's kind of far away, but one can include in the exchange process, which will modify the Kitaev-Gamma and Heisenberg. All of those, strengths will be modified. And that has been done by Guignard, by the way. So in fact, that the Guignard has taken into account the EG state and take that in the exchange process. With the field, I don't expect that those things can be drastically modified because it's a much high energy scale. And the field that we are applying is very small. Yeah, so.
Okay, thanks.
Yeah. Maybe I think the field is gonna be something important with the interlayer couplings, chemistry point of view, as Stephen has asked.
All right, thanks again for this very interesting discussion.